Welcome back. In this lecture, I will start with kind of a topic which is slightly different from the topics which we were trying to cover. So, in this lecture, I will go through intermolecular forces and molecular basis for corresponding states. Let me start with a very popular equation of state which we have been taught earlier, that is a virial equation of state. It has an origin from statistical mechanics. So, a typical virial expansion of the equation of state is given by this expression, okay, where P molar volume divided by RT is 1 plus summation of B divided by molar volume to the power n, where n ranges from 1 to infinity, where B is nothing but the virial coefficients. Okay. So, essentially this is B2, B3, B4 and so forth. Okay. Now, virial coefficients has origin of statistical mechanics. It is not arbitrary, and this is directly related to the molecular number of molecules. So, that means B2, for example, relates to the contribution of two molecules, that means a pair of molecules. B3 would be 3 molecules and B4 is 4 molecules. So, these are the contribution of individual clusters of different sizes to the properties. So, the way it is represented in statistical mechanics is that B2 is basically nothing but two particles connected by Mayer bond, which is given by function f. F is nothing but Mayer function, which is exponential of minus beta. Beta is nothing 1 by kT, and U is nothing but the potential of energy between these two molecules or two atoms in this case, and this is given as the B2 is given as double integral of F1 to dr1, where I is a vector, dr2. So, basically you are integrating this Mayer function as a function of distance r between these two from very small values to infinity around the space, okay, and that is why also normalizing by this volume V. You can extend this without going into the details. The B3 has 3 Mayer bonds, okay, where now 1 2 means that we are considering U12 in this expression, okay, and similarly B4 will have contribution from 3 different type of cluster containing 4 particles having Mayer bonds as depicted in this solid line here. Okay. Now, Mayer function is not exactly the potential function. It depends on this function, though it depends on this potential energy, and thus it is different from the typical potential energy. So, it's if you plot it this function as a function of r, it looks like this function. Okay. So, that means there is certain contribution where it is 0. So, if you multiply this one Mayer bond by another one, if one of them is 0, of course, the rest the contribution is going to be 0. Okay. So, this is how we express the coefficients in terms of the Mayer functions, and if you can express the Mayer functions in terms of the potential models, then you can evaluate numerically, analytically these virial coefficients. Okay. However, the difficult part is expressing the potential models. So, that is why the model potential comes into the picture, which we are going to talk little later. Or let me also explain how this B2 gets evaluated experimentally. Now, if you can look at this equation again back here, okay, this is the virial expansion, or this is a virial equation, and you expand it in terms of B's, and this is nothing but, if you look at it here, this is nothing but Z. So, if you multiply, if you take Z minus 1 multiplied by V, you are going to get this expression, okay, whether these other terms are higher order terms. Now, So that means the first equation can be rearranged to get this equation easily, because PV by RT is nothing but Z. So Z minus 1 multiplied by V is nothing but B2 plus B3 plus B4 by V square and so forth. So if you ignore higher order terms, then you can try to exploit this expression to evaluate B2. And how do you do that? By considering V, molar volume infinity of 1 by V to be 0. That means we are talking about extremely dilute or very low density systems. So this can be easily evaluated, the B2 can be easily evaluated for very low density gas by plotting this Z minus 1 V as a function of V molar volume, and you can extrapolate the values in order to get B2 for very low value of V's, okay. And this, so and the limit of V infinity of 1 by V which goes to 0, Z minus 1 V is finite, and this is equal to B2. That is what we are talking about. Once B2 is measured, we can measure B3 by again rearranging. So you can take out the B2 here. Now again you look into this and you can get it. Of course, this is only at a low density gas, and we know that as you increase the number of cluster, that means you are interested in more number of particles, and that means there would be error associated with this approach for the higher order virial coefficient, okay. But for the B2, it turns out to be a very nice approach to obtain from this experiment. Now the question is, now how good is this virial equation of state, okay. Now the virial equation of state also depends on the number of terms which you could add, but typically if you consider only up till third coefficient, it is a very reasonable approximation for low density gas. Now you can express virial equation of state in terms of density, okay, or in terms of density or in terms of the pressure, okay. In that case, the B dash, the B's which are typically, which we expressed in terms of the Mayer function, this is B's and C's, and dash are basically when you rearrange in terms of the pressure, okay, where rho is nothing but 1 by V. Now we can see clearly is that when you plot Z as a function of molar density, so this is nothing but 1 by V, okay, that was also the last one, okay, this was also 1 by V here, okay. So if you look at it, this is the experimental one, okay, Z decreases and this increases as you increase the molar density, okay. Now the one which is based on density is very close to the experimental values, whereas the one which is based on pressure deviates from the experimental value. So the density explicit equation of state, virial equation of state, is superior due to the compensating errors. That is something which we are asserting here rather than explaining it in details, but this is far better superior equation of state, which is better than the pressure one, but is also applicable to a moderate density, as in the case of this virial vapor liquid equilibria or vapor solid equilibria, okay. Now what are the features of virial equation of state, okay. You can have this pressure explicit, you can have density explicit. These are the exact theoretical basis in statistical mechanics, okay. The limiting form that all equation of state must approach at the low density. So this is, it tells you that the first term, when the 1 by V goes to 0 here, this is exact as, and this is something which all theoretical, all equations are much approach to that. The other thing which is very interesting, is important, is that the virial coefficient only depends on temperature. This is very accurate for gas only, and it can address the gas phase clustering by using virial equation of state. You can try to explain that as well, okay. So let me now touch upon the most important part of this lecture, is the intermolecular forces. Now invariably the intermolecular forces governs the way the particles behave, and collectively when the behavior are in some way you get a certain property, and the behavior in other way you get a different kind of properties. And thus it is important to understand how to come up with a model, potential model, which can represent the systems in a way which you can characterize the experiment very well, and thus in a reverse way you can understand how the particles interact and quantify various different properties in terms of intermolecular forces. Now let me define first this, okay, and now we are going to change the little bit of terminology here, okay. So the first important thing is one must understand that the interaction energy between two molecules not only depends on the distance between them, but as well as how they orient among themselves, okay. That means they depends on r as well as omega. So let me first define, let I symbolize both Ri, which is the position of the center of mass of the molecule, and Wi, the set of the Euler angles specifying orientation of molecule I in space. So in that case we are defining the intermolecular potential between particle 1 and 2, 1, 2 as gamma 1, 2, which is nothing but gamma R1 comma R2, and that will be the difference between these two particles, between the difference between these two positions, okay, in space. Now this is what typically we use that, okay. So since in the space this is our interest, then this may be R1, this may be R2, okay, but our interest basically is nothing but this, which is nothing but R1 minus R2, okay, and the modulus of that. Now what are the different types of interaction between two molecules? Let me first summarize that. So the one is electrostatic interactions, okay, which is mainly because the particles or the molecules will have charges, okay. Now so if you have charges or ions and between, and if there is a permanent dipole, quadrupole and higher multipole, then it will lead to electrostatic interactions, okay. Now in addition to electrostatic interaction you will have induction interactions. This is between, for example, a permanent dipole and an induced dipole. So we will come back to this individual contributions or interactions in detail, shortly. In addition to induction interaction, you will have dispersion interaction, very commonly available among the particles or molecules, and is very important interaction. This is a long range interaction that has its origin in fluctuations of the charge distribution. Essentially it means that the molecules may be neutral, but even if it is neutral, due to the fluctuations of the electronic cloud, it can have dispersion interaction. That is what we are going to understand shortly. In addition to dispersion, we may have valence interaction, which is nothing but repulsive interaction at short range, okay, which arises from the Pauli's exclusion principle. Now at the end we may have this residual valence interaction, which is a specific chemical forces giving a rise to association in the complex formation such as hydrogen bonding. So two molecules may have not just one kind of interaction but many kind of interaction. So we can summarize it, the total interaction will be due to the electrostatic, induction, dispersion, overlap and chemical, okay. So let me start and explain each of them. Now electrostatic interaction is something which is very well known, given a charge or the permanent dipole, okay. This is the case for the molecule having charges here such that it is a permanent dipole, okay, and this is the distance between them, this is again the other one. It has a specific orientation. So the way we have written is basically theta, which is the distance between these two center of mass of the molecule, okay, which is r is the distance between the center of mass of the molecule. Within the molecule the charges are connected by this length and is given by this dipole, okay, and of course dipole moment is this mu is equal to E multiplied by the d, okay, which is here from here to here, okay. Now what we can write is, if you do this calculation of using the Coulombic interaction, okay, and sum it up all possible interaction between, because you have charges here, 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 so there are many possibilities. So you would have to add up all these Coulombic interactions, and then the expression will turn out to be this. Okay. So this is the final expression, which not only depends on the dipole moment of molecule 1 and 2, but as well as the theta I and theta j, which is making with respect to the distance between the axis of the vector connecting the center mass of these two molecules. In addition, you have this phi I and phi j. Okay, this must be phi j. Okay, which is nothing but between this. Okay. So I do not expect people to remember this, okay, but something, the idea is behind is that to understand that these are the complex equation which turns out to be, and there is a rigorous means to obtain the expression. Now let me summarize some of the values which we have for the different molecules. Now we are talking about the permanent dipole moment, which will lead to electrostatic interaction. So you can see that we have summarized carbon monoxide 0.1 dibyl and so on. Those SO2 is very strongly polarized molecule 1.61. If you look at the water, again very polarized 1.84. HF is highly polarized. KBr 9.09 kind of molecule. Now similarly to the permanent dipole, we may have this quadrupole moment, which may be very small compared to the dipole, but is also relevant, and this is something which we will learn a bit later. And these are the values we can see. This H2 is 0.22 plus 10 plus 5, these are minus. Now the way we make use of quadrupole moment, it can also lead to negative values of it. Okay. So let me in general summarize. So you may have various different contribution of electrostatic. You can have charge, simple Coulombic interaction, okay, because of this. You can have charge dipole. If you have a permanent dipole, it can have this. You can have dipole. If you can charge permanent dipole quadrupole. So that means all these possibilities can occur for a given set of molecules, okay, leading to a very complex electrostatic interaction terms. Let me just try to explain a bit related to its arrangement. So if molecules are uncharged, then of course you can have the charge interaction will be negligible or will be 0, only the dipole or other contributions will come. If the molecule is non-polar, okay, in that case it does not have a dipole, but it can have quadrupole interaction. That is what it can have like this. For polar molecules, lowest energy configuration is tail to tail. This directly comes from the expression which we written here. And for linear quadrupole such as this, the lowest energy conformation is a T conformation. That means you have one molecule like this, another molecule like this. Okay. So these arrangements comes clearly from these energy values which you can plug in these thetas, the way it is arranged, okay, and you can clearly see which particular arrangement will allow the lowest energy conformation. The other thing is important is the temperature. At low temperature or for molecules with a large dipole moment or quadrupole moment, the electrostatic energy can have significant on the structure and thermodynamics, because energy or the arrangement of the dipole and the orientation gets significantly affected by the temperature. At high temperature and low density, molecules rotate freely and rapidly, so only symmetric part of interaction is important. And this means that you can consider the mean value of these interactions by integrating across the volume and the orientational space. Okay, so if you are considering typically average value, you integrating the orientational space, if it is, let us assume that freely rotate, that would be the case for high temperature. So, if you freely rotate, you just consider for the case of average potential. So, we are looking at only the Boltzmann factor, as we know that this is the most important part as far as statistical mechanics is concerned, and this is the term which provides you the probability of the configuration, and thus we are more interested in basically this part. Okay. So, so this is, you can consider this average as simply the average of this, okay, where we are dividing by this for normalization. Now, this part you can show without showing all the details that the average energy divided by kT can be written as in this form, where you have minus 1 by 3 kT, mu1 square, mu2 square, 1 by r6. This is the dipole part, or for the case of dipole quadrupole is this, and this is the case of the quadrupole. Now, so that means if you plug in this information depending on which part you are interested in, you will get these conditions for different combination. So, it tells you that the dipole is basically proportional to 1 by r6, dipole quadrupole is decays faster, quadrupole is decay much faster, okay. But nevertheless all are attractive, okay, and the important thing is the magnitude is proportional to the 4th power of mu or q for like molecules. So, this is what the average part comes out to be. Now, let me continue this and come to the case of the induced interaction. Now, so you consider this molecule 1, okay, and this is molecule 2. Now, due to the fluctuations of the charges, there is a transient electric field which gets around the molecule 1, and due to that, okay, field, there is an induced dipole in molecule 2. Okay. Now, the induced dipole is given by the alpha multiplied by the electric field. Okay, let me restate this statement here. Now, due to the permanent dipole here, there is an electric field in around molecule 1, and due to that it induces transient, or it induces a dipole moment in molecule 2, which is given by this expression. Okay. So, now you have a case of permanent dipole or permanent quadrupole and induced dipole here, and this is where you can get again expressions of this which you can come up with. So, I am not going into details of how this has been evaluated, but what is important that this expression exists. If you have such a case where you have permanent dipole, then there will be induced dipole, or if you have a case of permanent quadrupole, then the other molecule will have induced dipole, okay, and this is the contribution due to that. So, let us consider, and of course, most important thing is that the induced dipole depends on the polarizability. If you have a highly polarizable molecule, you will have large value of induced dipole, and this is the case here. This is the average polarizability, okay, and you can see this has varied information here. So, for example, in the case of naphthalene is a very high polarizable, that means it will get very high induced dipole here, okay. On the other hand, your water is here, argon is here, these are very small values compared to CCl4, C6H6, anthracene and so forth, okay. So, that was induced interaction. Now, let me come to the dispersion interaction, okay. Now, a dispersion interaction is relevant for the case where you do not have any polarity, or that means that it is for relevant for non-polar molecules. So, oscillation and distortion on electron cloud around nucleus means that even for non-polar molecules, the molecules can have non-zero dipole moment over a short period of time. Okay. The way you can understand is that you have a molecule 1 which is basically non-polar. The electronic cloud will fluctuate, and because of the fluctuations you will have a transient electric field or transient dipole which will cause electric field, and this will induce dipole in the molecule 2. Okay. But remember that if you take the average, over an average there will be the mean values of this is going to be 0, but as far as the dipole is concerned. So, rapidly changing, the dipoles can have rapidly changing in magnitude and direction, and thus average value of the dipoles will be 0, but nevertheless due to this there is induced dipole, and then you have this interaction between them, okay, which we call it as a dispersion interaction, also called as also known as London forces. Okay, so what are the values here? What are the expression which is for this London dispersion term or dispersion interaction is, it depends on the polarizability of molecule 1 and molecule 2, okay. So which is obvious, because you are creating a dipole moment for a non-polar molecule, and this also depends on this Planck constants, okay, and characteristic electronic frequency molecule in unexcited state. So this is the amount which to take out, this is the energy to take out from the ground state basically for individual molecules here. Okay, so how do we come up? We approximate, how do you simplify this expression? We approximate this h nu by this I, which is the first ionization potential for the molecule. Thus this expression turns out to be I1 I2 divided by I1 plus I2, and this is the polarizability. Typically the ionization potential does not vary much from molecule to molecule, so we can consider this to be a constant K, and that is where it turns out to be this. So for the case of a same molecule, it will be 3K divided by 2R6 alpha I square. For the mixed case, okay, between 1 and 2, it will be alpha I alpha J, and thus we can use this information to come up with a mixing model, which means that if you are interested in obtaining the potential model of due to dispersion between 1 and 2, you can approximate this as a geometric mean between 1 1 and 2 2, okay, and this is nothing but the Berkeley rule. In general, because this is an approximation, okay, in general the dispersion term will have not only this A by R6, which is this case, but as well as the other terms also, which usually is very small but is relevant. Okay, so let me just try to give an idea that what is the order of this dispersion with respect to the induced and dipole interactions. Okay, now of course the dispersion term depends on ionization potential, which is, you can see that it is not much varying, but in some case it does have significantly different from the other one. Now if you consider the intermolecular forces between two identical molecules, which is this CH4 CCl4, now they don't have, let's say, any dipole, but they will have strong dispersion interaction all in the same units. CCl4 again doesn't have any dipole, but it has strong dispersion, almost 10 times higher than CH4. Let's consider S2O, it has a dipole moment, and that's why it will dipole contribution, and then it will have also induced induction contribution because it has polarizability, okay, and it has a dispersion interaction. Definitely dipole interaction is much more than the dispersion, but it is also relevant. Okay. Now let's consider case of relative magnitude of intermolecular force between two different molecules. Let's consider this. Okay, here both of them doesn't have a dipole, so you have very high order of dispersion because of the fact that this has a higher and because of the fact that this has a strong polarizability. Now you consider S2O SCl, okay, both have dipole moment. Dipole is this, induction is this, but it has also very strong comparable dispersion interaction. So it tells you that the dispersion cannot be ignored, okay, compared to this dipole for many set of molecules and combinations. In addition to this dispersion, we also have to consider the valence overlap or repulsive interaction. So molecular beam experiments indicate that except at r equal to 0, that means when the particles are close by, for spherical symmetric molecules we can approximate this potential for overlap as simply a constant b multiplied by exponential minus another constant small b r, and this is sometimes also called Morse potential. Okay, so it has an origin due to the overlap of electronic clouds and Pauli's exclusion principle. In practice, we often approximate by a power law like this. Okay. So at this point, I will stop here, and now what we are going to focus in the next lecture is the different kind of models, okay, to appreciate what we have just learned, okay, and hopefully you will get more clarity on this model and as well as the kind of interaction, okay, when we are going to cover the different types of models in the next lecture. Okay. So, I will see you in the next lecture.